So yeah, thanks for joining us and being here so early. Hopefully those coming from East don't feel too bad, but thanks anyways. And first, I would like to point out that indeed our field is growing, as we've probably all seen these kind of plots showing the growth of registrations. And as a result, I think we're not quite figured out how to handle registering thousands of people in such a short amount of time. So, you know, there's, for those coming in maybe a bit later, we'll obviously put slides and so on, so hopefully they don't miss too much. But yeah, otherwise, welcome, and thanks for maybe queuing very early today. It's great to have you here, and we're very happy to be talking about deep learning, practice, and trends. We're gonna first, actually, we did a bit of a survey on Twitter, actually. So we asked what people kind of want to take out from tutorials. And we found most people are actually interested in the kind of bleeding edge research, which sounds a bit counterintuitive given this is a tutorial. So we're gonna try to have that second part about the trends, which talks about more recent works that we'll try to explain you in depth. However, the first part, the practice part, is gonna be more about giving you a gist about deep learning, about all the sort of tools available to a researcher or a practitioner in industry alike, on how to handle basically getting into deep learning and just understanding what entails to get a model into production perhaps, or get a research idea and trying it out and so on. And then the second part will be about trends. We picked here 5 trends that we consider are or have been important in the past years or will be important in the next few years. Obviously, there are many more trends and we cannot cover all of them, but we're definitely happy to discuss these during the questions, perhaps. So let's then begin. And I like to think of deep learning as a toolbox enabler. So there is basically a gigantic source of papers, source code, tutorials. I think this is great. It lowers the barrier of entry tremendously. And the way you can see this is you have all these tools available to you, frameworks and whatnot. And perhaps at the model level, you get to decide certain aspects of your neural network architecture. Maybe how do you optimize it? What is the task? What are the inputs? What are the outputs? And you put these together, you piece this together, and there you go, you have a model. You can obviously also zoom out a little bit of this picture, and there are other choices that are also quite important. For instance, even before thinking about the model, how are you going to train your model? How are you going to deploy your model? You can have specialized hardware, you can have generic hardware like GPUs, CPUs. You can also decide to do so in a cloud-based approach. And so these decisions might actually affect quite a bit what your model looks like or what you can do in your research. So these are very important early decisions to be taken. The second of which probably is the framework. So there are many frameworks available, almost too many it feels, but you have to sort of understand a bit what are the differences between these frameworks. Perhaps maybe more importantly, as a researcher, these frameworks might limit you in some way on the kind of things you can try easily. But also for deployment and whatnot, some frameworks may have better tools for certain platforms and whatnot. So all these decisions are quite crucial to get right, otherwise you might later on regret them. And lastly, there's a vast amount of data sets that you can decide to work on. Obviously, if you want to deploy something and you have a company, maybe you have your own data sets, but also deciding what those look like, how big they need to be, and so on. They're all quite important decisions, right? So this is sort of the zooming out on the aspects of deep learning. And obviously, we can also go the other way and zoom in. And if we zoom in, you start seeing sort of the life of a practitioner or researcher. So there are many choices, starting from neural network architecture details, like what nonlinearities are you going to use? Also optimizers, how do you optimize your model? This is really the engine, the core of what you're going to try to do here, which is get the weights to settle onto having a very low loss or high reward. There are things like connectivity patterns and so on that you have to choose and mix and match perhaps. The loss you choose also is quite important, and we are seeing through especially reinforcement learning quite a variety of losses that do not need to be differential anymore, And so you can really, truly optimize things end-to-end, which is quite great. And then perhaps the elephant in the room, which I'm not sure anyone likes here, is hyperparameters. This is really like crucial to make models work. And the list goes on and on. It kind of goes off slide, so you don't see many of these. But they're really important choices. And deciding, tuning these is kind of a part of your day-to-day almost if you do train many models. And so all these and many more are sort of details that once you get into deep learning, you have to start caring about. So for the talk, we're going to try to use this notation, so to speak. So we're going to talk about a few topics. And generally, they are either about inputs and outputs, about architectures, or about losses. So you'll relate these in the slides. And it might be useful to kind of always keep in mind this part of the talk. What is it about? Is it about a loss? Is it about a modality that we haven't been able to use before in deep learning, and so on and so forth? So let's start perhaps by sort of very basic things that we were doing with machine learning. And they're still very important and very relevant, which are like sort of what I call vectorized inputs. So these maybe perhaps the most classic data set which many people maybe have used, especially those who are, have maybe trained super vector machines and other kinds of models. There's the UCI machine learning repository. And these are like basically a mix of perhaps continuous and categorical attributes that you need to make predictions from, right? So here it's an example of a data set called adult, and you get to see things like the age of a person, their education, whether they are in a relationship or not, and then you can predict any other attribute from this data set. Perhaps you want to predict their income. So this is a very simple supervised learning task. And the input is sort of a bit unstructured and mixing these sort of continuous categorical things. And honestly, neural nets perhaps they're the least suited for this kind of data sets. Lots of things like SBMs or boosted decision trees and so on are perhaps state of the art nowadays. But what neural nets and deep learning really started to make good progress on is these kind of more structured perceptual, perhaps, signals. So images are much higher dimension than the UCI repository data sets in general. And you can do all sorts of things with images, as we know. So we've seen many of these examples. And for instance, there you have like a classification problem where you want to classify these onto 1,000 classes. This is ImageNet. We've seen a lot of very cool progress on generative models, like almost unbelievable how good these models have gotten, where a model is just training to reproduce the modality that you give it to it. So these would be, you give it celebrities' faces, and the model understands the joint distribution of all the pixels and is able to sample realistically looking images. And also some applications that were quite surprising to most of us, and I think this is why this field is so great, because there's so many people thinking about maybe novel applications that we perhaps haven't thought about. So I love this one where you basically do style transfer, where you take, a picture and then a style, perhaps photo like this bread-looking thing, and then you can combine them. And this actually is perhaps one that is commercially used. There's apps that you can do this, and people have lots of fun. It's perhaps a Photoshop empowered by deep learning, and I think we're seeing more and more of these sort of applications, which is quite great. And then perhaps the modality that I've worked personally more on is sequences, and sequences in a way extend images, because you can think of an image as a sequence, and also obviously you have videos which naturally are sequences of images, which themselves are sequences of pixels and so on. And text also is kind of an important domain that deep learning sort of took a bit perhaps longer to get really state-of-the-art and being deployed in production. And also some other things that are quite fun to work with, like programs and sequential decision-making problems that inherently have a sequence underneath. So maybe to finish this sort of section on input and outputs and so on, I'm going to just maybe give some sort of generic advice, which is, so when you're faced with a new data set, you typically have an idea, or perhaps you just want to train a baseline model. And what you have to do is first make the model run. So this could be like from compiling your code to the graph in a framework to be having not cycles and so on. Then you want to run this model and see the loss going down. And perhaps more and more we see people using cloud services to then do the maybe annoying or slightly difficult hyperparameter search, which is so crucial for deep learning. And then you iterate there quite a bit. And if you're a researcher, you might want to write a paper. If you're an industry, maybe you deploy your model and so on and so forth. But this is definitely the steps to sort of see something succeed in not even deep learning, just machine learning. And it's important to sort of, obviously this is simplified, but it's important to understand this. So I'm going to start with sort of explaining 3 key building blocks that are going to be used heavily in the more advanced trends section. The first of which is convolutions. And perhaps all these architectures, in retrospect, have these common characteristics, which is they have the right inductive biases, right? So in deep learning, we don't like to maybe have hand-tuned or engineered features. But what we definitely want to have is this inductive bias. So I'll repeat this word a lot during the talk, and I hope you will relate to this. So, but before getting there, here what we're talking about is perhaps the simplest form of image classification. So the inputs are going to be image pixels, the outputs are going to be perhaps a class label. The architecture is going to be obviously centered around convolutional neural networks. And the losses are fairly standard losses about cross entropy for classification, or perhaps you're going to regress to a continuous target and whatnot. And convolutional nets have been around for quite a long time. Perhaps how I learned about them was actually through this paper, which is very cool and has very good results on MNIST. And maybe things were a bit complicated when I started working on machine learning, such that these frameworks did not make it possible to just train a model on some data set in literally like 10 lines of Python code. So it was a bit overwhelming to work with these models, I think, in the early days, as well as not having GPUs that are so good at computing these sort of patterns of computation that I'll explain in the next few slides. So as I was saying, the key sort of invariance or inductive bias that convolutional neural networks have is this idea that in images, we care about 2 sorts of invariance. One is locality. So we believe that things that happen nearby in pixel space are correlated and form a group, so to speak. And also that, and this is application dependent, but generally, whether something is on a position like top left or bottom right, it shouldn't change too much, at least in terms of knowing what the object is, right? If you move the object, it's still the same object. And these 2 invariances are very critical. And when you design the architecture, that's precisely how you go from a fully connected architecture, which is shown here on the left, that would essentially connect all the pixels to the next layer, and it would not make use of these inductive biases to these sort of convolutions that first you can start by saying, well, let's not think about convolutions yet, but let's make the output of this would be the output of the next layer. So for instance, this green point does not connect to all the points in the image. This is an n by n image. It only connects to, let's say, a 3 by 3 region on the top left. And then this purple one connects to this 3 by 3 region, and so on and so forth. So there are actually, these are not quite convolutions, but they're almost convolutions. And this model actually was used at some point as well. It was untying the weights in a convolution, essentially. Although this is not so good for GPUs, because then if the weights are untied, you cannot batch so many computations in one sort of kernel call. So the second assumption that you say is, whether you are on the top left or bottom right, I want to use the same sort of filter to analyze this image, and this filter would be these weights denoted here by these lines. So by means of tying or sharing the weights, you get what a convolution in 2 dimensions look like, and that's why they have this name, obviously. And then just to be kind of more specific to understand what this means is you have an input that's perhaps 4 by 4, so this is a very low resolution image. And then with a 3 by 3 kernel, you create a second image that's 2 by 2. Here we assume no padding and no stride and so on. We're not going to go into much detail there. But this kind of operation is first very parallelizable on GPUs, which is great. And secondly, it has these right invariances, which help the model learn quite a bit. And just to extend or to actually explain what a convolutional network is, generally you don't have a single plane input and a single plane output. You generally have many planes as inputs. For instance, you have RGB channels, and later in convolutional neural networks, you have these feature layers that might be like 16, 32, and whatnot. And so, but this is all fine because all you need is to just create a matrix multiplication that instead of 3 by 3, in this case, would be 3 by 3 by 3, right? So here we have 27 filter weights. And that's basically like the building block of convolutional neural networks. And obviously, you can also have several output channels, which is quite useful in most cases. You do want to sort of expand the image from the 3 color channels to perhaps channels that eventually will become class discriminant and so on for classification. So if you put all these together, you just stack many layers of these convolutions. This is a particular architecture that does this, namely ImageNet. And you also have some pooling layers, which are essentially convolutions with fixed weights that just sum these 3 by 3 patches or sum maybe across all the inputs. And what happened, which was quite amazing, we already knew it was very good for MNIPS, but on ImageNet, this really made a discrete jump in performance in basically on this very important competition that was being done every year, including this year. So, and this basically allowed researchers in computer vision to test themselves with standardized benchmarks that also you didn't have access to the test data. So it was really like a very well run and well thought idea of testing progress in machine learning. And the first architecture that used this idea of convolutional neural networks was in 2012. And it really reduced the error rate from 28%, 26%, which seemed to be like kind of a pretty mild slope, to really reduce the error rate significantly. And ever since, the error rate has decayed quite substantially to levels of almost like humans' performance in terms of detecting these 1,000 classes. So ImageNet, I described it before, but it's a very important architecture. It really put deep learning perhaps in the mainstream, although me personally, I knew deep learning was very good for speech recognition, which was actually a bit before computer vision. So that was 2009, this was 2012. And the other thing that happened is that just by the means of adding layers, every year this competition was basically seeing reduced almost at a rate that seemed unstoppable, the error rate, right? So it went from 16 to 11 to about 6 or 7 to 3.6, and even now it's sub 3. So really the revolution of depth was very clear for images, and this is very important. But training a deep net is not easy. So I'm going to describe a few things that made this possible that perhaps if you just did this naively and when ImageNet was proposed, it wouldn't have worked right away. The problem with depth is twofold. One is computationally things get expensive. You can parallelize convolutions because you use the same weights in this manner of moving them around in the image. But depth you cannot parallelize. Depth requires to compute the previous layer and so on. So the sequence of computation cannot be parallelized easily. And as a result, things get slower as you increase the depth. The second issue, which perhaps is more fundamental because people were maybe willing to wait for a bit long to train these models, is optimization. Optimizing these models is not easy. And in fact, there's lots of issues with vanishing gradients and so on that also present in recurrent neural nets. So to deal with perhaps the depth and the computational issue and also the explosion of a number of parameters, people basically nowadays use almost only exclusively 3 by 3 convolutions, which if you stack in depth, do a more like a larger receptive field of 5 by 5, 7 times 7, and so on. So in this way, depth gives you, for a fewer parameters, a larger receptive field than if you just had to have a 7 by 7 convolution. So this insight is very important. We see this in a lot of architectures nowadays. And then optimization-wise, there was batch normalization, which was also pretty critical in the times of inception. And then also all people started investigating all sorts of tricks to do weight initialization properly and so on. So these were kind of perhaps some breakthroughs that we had, and then later on, the idea of residual connections came about, and it really also enabled us to train this model much more easily. So this is just putting sort of Inception, which has some very clever ideas on how to set up the architectures with batch normalization. And here you can see in blue, like you really get much faster training. So this was maybe the times where we work a bit on both modeling and also optimization jointly. And then perhaps even more impressively, because it's even simpler, is the idea of adding residual and skip connections to your model. And the idea is so simple that it fits in this slide, which is you have these deep layers of convolutions. All you have to do is skip, namely, instead of having the output of this small neural network here be f of x, which would be like a bunch of maybe 3x3 convolutions, you have it to be f of x plus the original x. And that simple idea works very well, not only actually on convolutions, but also on residual LSTMs and all sorts of related ideas. There's highway networks, also a very interesting approach that's kind of the same idea of skipping ahead computation. And this really enabled something that if you just tried naively wouldn't work. So here is without residual connections, if you go from 20 to 32 to 44 to 56 layers, you see the training loss is degrading, which is something that mathematically is not possible, because a neural net that has more expressivity, it has more depth, should be able to generalize a network that is shallower. But it was not possible to train without the residual connections. But voila, when you add these residual connections, you get that adding depth actually adds performance in training, and also luckily it generalizes to the test set. So this was a great result, I think, and very simple and very influential, and it also reduced the error rate again by half in 2015. And with that, kind of ImageNet is kind of a benchmark that is really, really getting so good that I believe the competition might not be run anymore, or there's other challenges that might be beyond classification that people are going to consider in the field. There are two related ideas that I will just quickly explain just for completeness. DenseNet, this was a very good paper this year, which proposes to simply skip connections essentially between everything and everything. So it's kind of generalizing ResNet, but it actually works very well for classification and so on. And the other paper that's extremely cool as well is this UNet architecture, which proposes to skip connections in a neural net that essentially reduces the resolution as it goes through a bottleneck, and then increases the resolution again to do things like image segmentation. But then it adds a shortcut between the same resolution from the encoder to the decoder. So that's also very cool. So I'll leave this summary here for also when we put the slides, there's some additional resources. But I wanted to move on to another kind of, two different kind of data sets, or data that's like sequences. And so the actual model is recurrence and attention. So here, again, inputs and outputs can be images, actually text, audio waveforms. We've seen a wide variety of applications of sequences. And then the architectures are recurrent over time and or space, and they do have attention. And recently, we've seen a switch to attention-only architectures, which are pretty cool, and I think Scott will go in a bit more detail later. And then the losses, again, here are pretty straightforward, cross-entropy loss. So I think there's two key ingredients on what happened in not image, but language. And these are very important sort of almost discoveries that together have brought deep learning into a toolbox for natural language processing. The first of which is to embed. So in text, we have these inputs that are discrete. They're words, and there can be many words. We don't even have, we don't have a full vocabulary, so we can also go to characters and then describe words by sequence of characters and so on. But the key insight here, which is actually fairly straightforward in retrospect, is that a word can be represented as a one-hot encoding, right? So a word, let's say we have a vocabulary of size 10,000, we can represent this word as all zeros but 1, 1 at the position of the integer for which we decide to encode the word. And that is a very simple idea, but it's how we enable to go from this discrete representation to this vector space that we like our neural nets to operate on, like which are dense vectors that are maybe like 256, 512 dimensions, and so on. So that first key insight allows us to take text and convert it into a vector. That's very important. The second one is recurrent language models, which right away really outperformed other approaches for language modeling, which really kind of made enough empirical evidence that people started to believe in sort of recurrent neural networks and so on working very well for language. And for me, the first time I saw this result, which was amazing, was from Thomas Mikolov in Interspeech 2010. And to go a bit more in detail, the key insight here is to vectorize context. So we have a context of previous words. So for instance, here, the task is we want to predict that the next word in this sequence would be mat. And we have the previous words, which is the cat sat on there, right? So we're going to one-hot encode these words. We're going to embed them via a multiplication that obviously you can do very efficiently because this is a sparse multiplication. You don't do it densely, unless it's a very small one-hot. And then perhaps the simpler thing to think about is you encode a fixed length of words. Maybe you have a window of 5 previous words. You embed the words, and then you have now a 5 times whatever, let's say 100-dimensional embedding vector for the 5 words. So it's 5 times 100. And then you can have a matrix multiplication, pass it to a softmax that tries to predict what the next word is. And in this case, you have a very nice loss that you can set up, and you just go ahead, do that, and train a model, and you get fairly reasonable language model performance doing this. But this is a bit annoying because you need this fixed window length, and also it's not very natural. Like there's not the right amount of invariance here. So the invariance we would like to know is that as I see a word, I update the state of sort of what I believe the next word is going to be like, and I don't want to have this fixed length assumption, which is anything beyond 5 words ago, I actually cannot input in this model. So there's basically a very heavy Markovian assumption here. So recurrent neural networks sort of solve this issue in a very natural way, which is you're going to embed the word one at a time, but then you have a hidden state that you keep updating with as simple as a function as this one, for instance. So you take literally the word embedding, you multiply by a matrix, you take the previous state of your network, the hidden state, the memory, so to speak, and you multiply by another matrix. You sum these two together, apply a nonlinearity, and this defines the next hidden state. And then from each hidden state, you can also predict what the next word is. So this sort of operation you can repeat. And now, as you read words, you keep adding them to your sort of working memory, so to speak. And that enables you to have way more invariance and no independent assumptions that you needed otherwise. And so recurrent neural nets really are like state-of-the-art language models in terms of log probabilities that they achieve on test set. And then a slight extension to this is, well, we can generate language, let's say, unconditionally. But now we have a way to have this working memory read in a sequence and output a sequence. So there were a bunch of papers that proposed this in several forms and on several data sets. But people nowadays call this approach sequence to sequence. There was a tutorial at ICML, so I'm not going to extend too much on this. But the main idea is so simple that it's almost impossible not to show it, which is instead of generating the next word given the previous words, we're going to have as a previous word some sequence that we probably didn't need to generate anything from. So for instance, we can take French, read it all in the state, and then start generating the translation in English. And that was a very simple insight that thanks to the power of recurrent neural networks, people felt like bold to try and to sort of change the paradigm of what otherwise would be statistical machine translation. And in a nice way, and I alluded to this before, is that nowadays with these frameworks, there's very simple code that you can write to do all these kind of complicated architectures. So here, for instance, these few lines of Python code, you don't need to read it, obviously. These are represent the LSTM architecture, which was very critical for sequence to sequence and was introduced quite a long time ago. But the first time I actually knew about this in 2007 or so, it just wasn't possible to implement all the gradients and so on. It was quite cumbersome. Nowadays, it's as simple as either using a library or you can write it from scratch like there, and it's very simple. So definitely these frameworks have helped quite a bit. And as a result, maybe not as impressively as in ImageNet, but obviously convolutions had been around for much longer than ImageNet. But in neural machine translation, we see a similar trend, which from a strong baseline based on statistical machine translation to state-of-the-art, these are blue scores and higher is better. We sort of had the first sequence-to-sequence papers, which for single model, they didn't outperform state-of-the-art, although you could ensemble the models and they actually outperform. But then recently, we've seen more and more papers that by means almost of scaling up and adding attention, which I'll describe in a second, they actually achieve, they defeat sort of traditional methods. And of course, combining both is even better and so on. But these kind of switch the paradigm of in-machine translation to a neural approach, which was quite nice to see. But maybe there is a very strong limitation on sequence-to-sequence, which is when we designed it, we didn't think too much about this because we actually trained a very extremely large model. Like it had 8,000 hidden units. But there is a very strong bottleneck. And here I'm showing, this is from the paper that we wrote a while back, sequence to sequence, as a function of the sequence length of the input, right? So the more words you try to kind of put into the memory, you might think that this memory eventually will be overwhelmed because it has a fixed dimensionality. But our dimensionality was 8,000, which is quite large for neural nets. However, the other paper, or another paper from Montreal, saw that as you increase the length, you actually decrease the performance because the memory gets overwhelmed. And I believe their model had 1,000 dimensions or maybe 512. I forget exactly how much. So this was a problem, and you can visualize this problem by looking again at this graph, which is here you're encoding A, B, C, D into this box, which represents the vector of your hidden state. But everything here has to be now decoded to the target sentence. And this is a very strict bottleneck that perhaps is unnatural, and perhaps there's a way to have, again, a model that has the right inductive biases to extract or to translate or to whatever we need to do sequence to sequence. And that's precisely what attention does. So attention relieves this bottleneck and says, look, for translation, for some languages, it makes sense to think about translating parts of a word or words or multi-words onto other words. And there's a sort of an alignment idea, which actually statistical machine translation uses quite heavily. So this alignment between inputs and outputs, this network does not care at all. It doesn't have any structure that induces this alignment explicitly. Of course, internally, it might know that if I read the word cat, it should translate to the word gato in Spanish and so on. But there's no explicit alignment, right? Whereas this attention mechanism allowed you to latch onto this issue that there is a natural alignment between inputs and outputs, which is shown very nicely in this figure from Badenau et al. Paper from 2015, one of the best papers of the year, no question, because this attention mechanism is really like taking over in many other fields now. But the idea of alignment is like it's there. The model has the ability to align or to kind of attend to the input, but we don't actually have supervised data to know what should be aligned to which, what should be aligned to what. It just learns to align just by looking at a massive amount of data, which is extremely cool. So here you can kind of see an alignment that goes here reverse because French and English, they don't align monotonically all the time. And this was very cool to see that this was emergent from the data just by adding this way of inductive bias. So in the inductive bias, I'm going to explain the mechanism a little bit. It's quite simple. You take a sequence-to-sequence model, and then you add this sort of mechanism in between the encoder and the decoder that will allow the decoder to query the encoder at every time step for information that it might need to decode what word goes next, okay? So in here, this decoder has seen this word, which is start of the sentence, and it's going to sort of try to, from its own state, and from all the states of the encoder, produce a query and a vector that is maximally useful to predict the next word. And this goes on and on. So this F of input, all the inputs, and H1 goes for every time step here. And then how it's used, this sort of embedding that get almost reads from the input, gets that fed back to the decoder to predict X, and also it gets fed into the state because maybe something you read might not need to be read again and so on. And so this mechanism is very, very simple, and it's all differentiable, at least in the way that it was done in Badenau et al. And it produces these beautiful attention masks, and it also improves translation quality quite a bit, especially if you have a very small bottleneck, if your hidden states are not too big. So that's all I wanted to say about I mean, this attention mechanism, and just to be a bit more specific on how to actually do this. Say the inputs are, I am a cat. You have a word embedding or an LSTM embedding for each of the positions in this sequence, E1, E2, E3, E4, for each of the 4 words. And then the decoder at some point has a state HI. And then the way you do this is you do a dot product or some function that takes HI and takes all the inputs and computes a strength or an alignment or an attention over these 4 inputs. So in this case, a simple dot product, assuming the dimensionalities match and whatnot, is what some people do. And so you take this HI transpose times E1, that's a single number. You do this you have 4 single numbers that represent the strength of the connection on how this HI is querying which input. And then you simply normalize this with a softmax, which is again differentiable. And then you read out from the input something that's relevant. So you have this vector of strengths. They produce this strength vector like 0.0, 0.5, 0.9, 0.05. And perhaps for this particular HI, this is asking you to attend to the word A, because maybe that's the word that you need to produce next and whatnot. So it's a very natural mechanism, and it works really, really well. So this is again like sort of taking over sequence-to-sequence models, and it's been out there for a while. And so in terms of dealing with sequences, if they're very long, as I said, you can have a bigger state, but attention really, really helps. It has the right inductive biases. You can also have some tricks like reversing the inputs, which works in some applications like translation. And then, there's other tricks here. I'll leave them for the slides for you to read later. But they're sort of tricks of the trade almost, that if you deal with sequence models, LSTMs, and so on, you would definitely don't want to miss. And every paper should sort of ideally report these tricks in some form or another. And as a consequence of like these ideas of sequence prediction, sequence to sequence, and so on, a plethora of models came out that can do also, that basically they're kind of drop into your models. You can have, for instance, very cool things like read-write and memories, which was presented in the neural Turing machine. You have key-value memories, which was done at Facebook, which is very beautiful, where you can have a memory, but also attach it a value and so on. So there's lots of extensions to these, and I recommend you to read about them if you're interested about sequences and so on. And then I'll leave the additional resources. There was a full tutorial this year at ICML, so I didn't want to extend this section too much. And so we're going to move now to trends. Perhaps if you have a urgent question, you can ask now. But otherwise, we can leave it also at the end for questions. You remember sort of the section. But if there's a question now about convolutions, recurrence, basically like basic model components, would be a good time. All right. Otherwise, in the break, you can also come. So this is something that it's very hard to do, right? Like, so the next section will be trends. Of course, there are trends that we like as researchers to work on, and also trends that the community is sort of taking on. So one thing that we did is do this kind of source, the cloud word for like all the abstracts that were papers submitted at ICLR about a month and a half ago. And then, obviously, you identify the typical deep and neural and networks and learning and so on. And in black here, I showed things that I just discussed, like sequences, recurrent, attention, convolutional. These are pretty established methods right now. But there's some that we're going to discuss in the next section, like graphs, which are kind of maybe trending a bit now. Also adversarial, like obviously there's a lot of attention and interesting work being done in generative adversarial models. And generative models, which Scott will talk in a bit. And also there's other words that we're not just going to cover, because there's just been recent tutorials that did an excellent job. For instance, deep reinforcement learning is quite a hot topic, and you can see agent or like environment or reinforcement as words that appear a lot in abstracts in papers. And I suggest to go to the last year tutorial at NIPS, which was excellent by John and Peter. And with that, here, Scott is going to come up and talk us a bit about more of a trendy topics like autoregressive models. And then we'll take a break in a few, and we'll continue also after with more trends. But for now, I'll stay down there.
Okay, I'll talk about autoregressive models. First, I want to talk about where they fit in the landscape of generative models. There's many different kinds besides just autoregressive, so I'll just quickly go over them. So there's latent variable models like VAE and variations like the deep recurrent attention writer. There's implicit models like GANs that can generate samples but don't give you likelihoods. There's models that learn transformations, invertible transformations from simple distributions to, let's say, images. And then there's many different kinds of autoregressive models. So there's been a really good tutorial at UAI on deep generative models that cover the first three in a lot of detail. And also there's a NIPS tutorial from last year on GANs that you should check out if you want to dive more into those. I'll also talk about GANs more in the domain alignment section. But for this part, I'll just talk about autoregressive models. So what's the idea of autoregressive models? We want to make use of the chain rule of probability. So if we have some joint distribution that we want to learn, we can factorize it by ordering and possibly grouping the variables. And as long as we're consistent in this ordering and don't violate causality, we can learn the joint distribution. And each factor can be parametrized by some theta, which could be, for example, a deep neural network. And this can be one such theta per factor, or you can share them over the factors. And so the main modeling choice is how do you order and group the variables, and how do you parametrize each factor. So the building blocks that we'll be using in this section for the inputs and outputs, I'll talk about models for images, for text, for raw audio waveforms. And these things can be inputs to the model and outputs to the model. And you can also view them as conditioning variables. For example, some problems involve more than one of these, like text to image synthesis or text to speech synthesis. In terms of architectures, they really span everything we've talked about. So we have recurrent networks over both space and over time. Previously, we've mostly seen over time, or like over sequences of words, but we can also think about it in terms of sequences over like pixels in space. We'll use causal convolutions, convolutions with attention, and even architectures that only have attention, that they don't have any convolutions or recurrence in them. For the losses, you can use cross-entropy loss, or in the continuous case, you can use mixtures of Gaussians or mixtures of logistics. So first, audio. So here is just infographic of what a waveform looks like that we want to model. So one way to model these is to use causal convolutions. So the input to the network is just the raw waveform. For example, in WaveNet, you go through several layers of convolutions, and the key thing to notice is that each output only depends on inputs from prior time steps. So for example, this node is not going to have in its receptive field any information about the future. If you want to get more context for every prediction, an important tool is dilated convolutions. So even though the convolution kernel has the same number of weights, you can increase the extent of time that it is able to affect the prediction at any given time step. So with the larger your dilation rate, the more quickly you can expand the context that is used to make a prediction at a particular moment in time. This turned out to be very important for modeling audio. And you can also stack these things multiple times. So you have several layers of dilated convolutions where you have a schedule of dilation rates that repeat. So you can have 1, 2, 4, 8, and then several stacks of this repeating. So how do you train these things? So the simplest thing that you can do in terms of a loss is cross-entropy loss. So given the preceding observations at previous time steps, you compute logits over y, and these will be used to compute the probability of the intensity value being in one of each of the possible quantized values. And so you can do a softmax to normalize these, and then the objective is the negative log likelihood. And so in TensorFlow, there's a useful function, softmax cross entropy with logits. So this is the simplest thing you can do. But there's other ways. So one disadvantage of cross entropy loss is if you have many, many possible values, the memory consumption is very large. So a different approach was taken in this Pixel CNN++ paper where they propose a discretized mixture of logistics loss. What's the motivation for this? So on the left, there's a plot in that paper of the marginal distribution of sub-pixel intensity values on CFAR10. So this is images that were discretized with 8 bits. So there's 256 bins here on the x-axis, and you can look at the frequency of each pixel value appearing in the data set. So you see peaks around 0 and peaks around 255. And so they use a mixture of logistics loss. So here's the logistic PDF and the CDF. So you can see the CDF is actually a sigmoid function. So this is the same logistic sigmoid that you can use as nonlinearity in neural networks. So what's the actual loss? So we model the values that's coming from this mixture of logistics. And so you parameterize this by a mixture component pi and a location and scale parameter mu and s. So you model the data as being generated like this. And when you want to compute the likelihood, the probability of a particular intensity value x given these mixture of logistics parameters, all you need to do is compute the CDF at the right side of this bin minus the CDF at the left side of this bin. That tells you the probability that you assign to the intensity value being at x. To sample from these models, if you're using the standard WaveNet, you have to go in sequential order. At the beginning of sampling, you don't have any waveform, so there's nothing to depend on. So you have to actually do one network evaluation naively to generate one sample. And so you can see, moving from left to right, the sampling procedure. Every network evaluation gives you one more time point. So how do we speed this up? There was a paper that just came out called Parallel WaveNet, where you can distill a student network from a teacher network so that sampling goes from big O of n to big O of 1. The idea is that you can pre-train a WaveNet teacher in the usual way, and then train a student network, kind of like the generator in a GAN, that can take in noise as input and then generate all of the waveform samples in parallel. The objective function for this would be to get a high likelihood under the teacher's distribution, and also to maximize its own entropy. For more details, check out this paper on parallel WaveNet, and here's an animation of what sampling would look like. So now, instead of going sequentially from left to right in the waveform, you can just feed in the noise all at once and actually produce the waveform in parallel. So this is actually what's being used now. And here are some mean opinion scores showing that it's quite good compared to non-neural net-based systems, and it's fast enough to be actually used in production. So now I'll talk about modeling text. Similar to audio, it's just a 1D sequential problem. So now instead of modeling samples in a waveform, we can model words, or we can just model the characters in the text, or words and characters together, or even bytes and bits. So words are useful because they give us shorter sequences and their units are semantically meaningful. Character level, we have longer sequences independent. It's not semantically meaningful, but the vocabulary size is much smaller. So there's trade-offs between them. So I'll show how the receptive fields grow in predicting a word for deep RNNs compared to something like an autoregressive model like ByteNet or WaveNet. So one of the advantages for using autoregressive or convolutional autoregressive models for text is that the architecture is parallelizable along the time dimension. You don't need to unroll your RNN during training, so it can be a bit faster. And you can have easy access to many states from the past by using dilated convolutions, just like we do for audio. And so this can be plugged into applications like neural machine translation. You can also use causal convolutions in neural machine translation with attention. So there's a paper called Convolutional Sequence-to-Sequence Learning that came out recently, where in addition to having causal convolutions over the output sentence in the target language, at every time step, you can attend to the words in the source sentence. So unlike in the recurrent attention models, you can actually batch the attention. Because you have access during training to all of the target language words at training time, you don't need to depend on having done previous attention lookups to produce the next attention lookup. Everything can be done, everything can be batched at training time. You can also have models that are autoregressive over time that are neither convolutional or recurrent. So this was in the paper, Attention is All You Need. So this transformer model gives the inputs a positional encoding. And the only care you need to take is to mask this dot product attention over the inputs to preserve causal structure. So here's what this looks like, this self-attention procedure compared to what you would do in convolution. So in convolution, you have this kernel that you're sliding over the input to produce the features of the next layer. And it's always the same kernel with the same weights that are being trained. With something like self-attention, to produce the hidden unit activations at the next layer, you have access to the whole spatial extent of the previous layer, and the weights are actually adaptive. So you can see the shading of these arrows here can actually change depending on the particular inputs and outputs. So it's a much more flexible architecture, potentially. People have also done things similar to the WaveNet distillation for text. So there was a paper on non-autoregressive transformer networks for machine translation. The idea here is to use an old idea for machine translation called fertilities. So on the left, you see the input sentence. On the right, you see trying to predict the output sentence in German. And what they do is for every word in the input, they predict what's called a fertility value that says how many times this word will be repeated for the translation network. So if there has a fertility of 2, it's repeated twice. If this next 2 have a fertility of 0, they're omitted. And then you just basically learn a mapping from this fertility augmented input to the target sentence. And so you can actually do this in parallel. You don't need to model the causal dependencies over time. But the big question is, where do these fertilities come from? So one thing you could do is pre-train an autoregressive teacher network, like they do in parallel WaveNet, or you could train a model with attention and then use the attention values to somehow learn to predict these fertilities. But it's interesting that a similar idea that we use to do parallel sampling in audio can also carry over to text. So now I'll talk about modeling images. So it may seem like a strange thing to do with autoregressive models because we don't have this very obvious temporal structure like we did for audio and text. But then the question is, how do we come up with an ordering among pixels? So one way to come up with an ordering is just to do raster order or interlaced, like in this GIF, where you just decide on some kind of way of ordering pixels, like going from left to right, top to bottom, for example. Or you could do it group by group. So you have some way of grouping pixels and then ordering the groups. And you get different models from each approach. So pixel by pixel is the simplest way. So here's a familiar chain rule. And here the assumption is that every factor, this theta, is a shared neural network. So, for example, pixel CNN or spatial LSTMs use this kind of approach. And the key component that allows you to do this is causal convolutions. So on the left, you can see the spatial masking for a convolution kernel. So all the ones mean that information from the parts that have 1 will be passed forward to the next layer, and everything with 0s is hidden from the network. So if you want to predict, let's say, the pixel at the center value, it's not allowed to see anything from the future. In addition to spatial masking, the convolution kernels need to be masked over channel dimensions. So if you're predicting color images, you might want to make the green channel depend on red and blue depend on red and green, but not any other ordering. So what would the perceptive field look like? So if this is a big image, and this is one convolutional layer, if we want to predict this black pixel after one convolution that is masked in that way, it can see information from these 4 green pixels. And after doing several convolutional layers, you can see the receptive field grows to contain everything above it in the image and everything to the left. You need a little bit of care needs to be taken not to have any blind spots. And so the Pixel CNN paper goes into detail about how to do that properly. Okay, what about modeling images group by group? So the equation looks, for the joint distribution, looks almost the same, except now instead of a single pixel being predicted, you actually have a group of pixels depending on all previous groups. The group structure then encodes conditional independence assumptions. If you're factorizing it in this way, you assume that all of the pixels in the current group XG are independent given all the previous groups. So that's going to limit the expressive power of your model, but it will allow you to predict them in parallel. So there's this inherent trade-off in terms of your model. But if G is very small compared to N, then sampling becomes way cheaper than pixel by pixel. So how could we do this in 2D? So one reasonable way you could do this is to interleave 4 groups. So you could take the upper left, so divide the image into 2 by 2 blocks, take the upper left corners, and that's group 1 pixels, and then predict everything to the right. So that's group 2, and then everything to the lower left, and then the lower right, until you've filled in the whole image. So each one of these transitions can be parameterized by a neural network. So from group 1 predicting group 2, 1 and 2 predicting 3, 1, 2, 3 predicting 4. Each of those can be a neural network. So we went from O of n factors here to O of 1. But where do these group 1 pixels come from? I mean, if you predict all of those in parallel, it's going to be very difficult to actually produce compelling images. If you have enough context to model them as independent, then just generate them in parallel and it's fine. Maybe if you have something like a really detailed segmentation or previous frames in a video, it's feasible to predict these in parallel. Otherwise, you can deploy the same procedure recursively. So now we have to generate an image of half the resolution. And so we can do the exact same thing, factorize it into these 4 groups. And so if you do this procedure recursively, you'll end up with log n factors, which is much better than O of n in terms of sampling. We can do the same thing in 3 dimensions. So instead of 4 groups, you could have 8. And there was just a paper on this that was using autoregressive models for scan completion. So if you have some room, you can generate data by virtually scanning it and using a 3D reconstruction algorithm. Unfortunately, these things are filled with holes due to sensor occlusions. So then the task is, how do you condition on this and get back your clean volume of your room that you're scanning? So you can use these 3D autoregressive models for this purpose. And they end up doing a pretty good job at filling in sensor occlusions. And it's a scalable model. So to summarize about autoregressive models, we talked about fully sequential models that factorize it to per pixel or per sample in a waveform. So things like Pixel CNN, WaveNet, and previous autoregressive models. They typically have very fast scoring, like one network evaluation will tell you the likelihood of any image under your model, but sampling is O of n, sequential, because of the assumptions made by the model. If you make some conditional independence assumptions, you can reduce the cost of sampling to O1 or log n, depending on how strong your assumptions are. And then the new class of distilled models actually can have the best of both worlds. So this is like the parallel WaveNet or these parallel machine translations papers. They can have scoring may be more expensive, but if you don't care about scoring, you just want to sample, they can do very fast sampling. So there's kind of a duality between the simple autoregressive models and these distilled models. Okay, so now I think we'll take a break for 10 minutes. 10 minutes. Okay, this section I will talk about domain alignment, in particular unsupervised or weakly supervised domain alignment. So this, I think, is one of the most promising and exciting things that's happening in unsupervised learning. So what are the building blocks? So what I'll talk about, at least in these slides, the building blocks are sets of images with some shared structure, but there's no direct alignment labeling which pairs of images in one domain or the other correspond. And for text, you could think about text corpora in different languages but where you don't have matching sentences with the same meaning, but you still want to learn to align them over the two languages. So here in this section, the architectures I'll talk about, it's really nothing fancy. These models are all about hooking up pieces, like simple pieces, in clever ways. So for images, they'll be just convolutional nets. For text, we'll see pretty vanilla convolutional networks, maybe with attention. But the game is really to wire things together with a loss so that an alignment emerges between two domains. So these could be losses in the latent space of a neural network, where you want them to be indistinguishable to a neural network across two domains, or in pixel space, or in some raw observation space. There's things like cycle consistency that we'll talk about. And also what I find interesting about these models is that there's cases where adversarial objectives are used, and also where very simple maximum likelihood is used. And in several different cases, in very different models, you can start to see the emergence of alignment across domains without supervision. So what do I mean by visual domain alignment? So here's a few examples. So you could have these street view house numbers and MNIST digits. So clearly they're talking about roughly the same thing, I mean numbers. But the actual style and structure of the images is very, very different. So to a human, it's easy to see which ones match up. But to get a computer to get that without manually labeling it is very tough. Faces, we can think about photos of faces and cartoon avatars, or pictures of the same scene in day and night, or summer and winter, or photographs of buildings and sketches of buildings. So to humans, it's very easy to match these things up. There's been work on doing the alignment in a weakly supervised way. So suppose you have images, sketches, clip art, and other modalities that are talking about the same thing but have a different structure. If you have some kind of weak labeling, like what is the class of the image? Is it a cat or a dog? Is it a plant or a castle? That kind of thing. What you can do is have a modality-specific encoder followed by a shared set of layers that are shared across modalities. And if you just train this to optimize some downstream task like classification with some regularizers to encourage alignment across domains, what you can find is that this thing learns neurons across different domains that activate for the same semantic concept with no supervision. And then you can query the model. You can plug in, let's say, a photograph, and then retrieve very similar images in other domains, like clip art, or spatial text, or sketches. And in some cases, they even have very similar spatial structure. So there's actually neurons that are both spatially sensitive, that care about where these things are happening, and semantically what is happening, but insensitive to the specifics of that domain. So another approach people have used is adversarial learning. So suppose we have several domains. You share an encoder, here shown in green, across all the domains, and again there's some downstream task that's shared, like classification. And what we add to this now is a domain predictor. So we have a network that's trying to use these shared features to predict whether it's from the domain of photographs or from sketches. And instead of optimizing this thing, we actually compute the gradient and then flip it. So there's this thing called gradient reversal. And by reversing the gradients and using them to train the shared encoder, we end up learning feature encodings that are invariant to the domain. So even a neural network, as good as they are at function approximation, wouldn't be able to figure out whether it's a photograph or a sketch. And so by construction, you are aligning the domains. This was used for classification, but we can also do it for image generation. So in this setup, you could think about trying to learn an encoder-decoder architecture that could produce face sketches. and you don't have any actual aligned pairs of face and sketch, but you can do the following. You can learn an encoder F that can see both sketches and face photographs. Okay, we're good. The encoder, again, is shared over domains, but then you have a decoder that just produces sketches. So for the sketch that was input, you just want to make sure that you can reconstruct it. You encode it and decode it, you should recover. If you encode a sketch and decode a sketch, okay, you better get a sketch back, and it should look the same. If you encode Brad Pitt's photo and then decode, what you hope is that you get a sketch of Brad Pitt. So you can encode that again using the same shared encoder and make sure that the latents actually look the same. And then you can also pass both sketches to a discriminator that tries to detect whether actually the domains match, whether the domain of sketch or photo is distinguishable to a discriminator. So here's what some samples look like. So given a street view number, it can actually produce the MNIST digit that corresponds with it. Or given a face, it can produce the cartoon avatar of the face. And they're not perfect, but in many cases they're quite good. And it's quite remarkable that you can do this with no supervision for producing these really high resolution outputs. So now I'll talk about cycle consistency. So the idea here is we have two domains, x and y. We want to learn a function g going from x to y and f going from y back to x. So the property that you want to maintain is that if you translate from x to y and then y back to x, you should recover the same thing. So it's being shown in this picture. So you should make sure that these two blue points are close together in x. And the same thing for y. If you go from y to x and then back to y, you should make sure that those two red dots are close together. In addition to that, you do the usual domain classifier adversarial loss. So you have a domain classifier for y that tries to detect the difference between actual samples from y and generated samples from y. And you have a domain classifier for x that tries to differentiate actual samples from x and generated samples of x. And this actually works remarkably well. You can do things like translate zebra pictures to horses or summer to winter using these, what they're calling them cycle GANs. A similar but slightly different idea is in this paper called Unsupervised Image-to-Image Translation using encoder-decoder networks. So here, instead of doing cycles from like one pixel space to another pixel space, what they do here is learn a shared latent space. So take an image from domain 1, use the domain 1 encoder to get to some shared latent space z. And there's two paths that it can take. It can use the domain 1 generator to reconstruct itself, and it should just match. Or it can take the other pathway and use the domain 2 generator to try to translate it into the other domain. And then it has to go to a discriminator. The D2 discriminator will say, okay, is this from D2 or not? And it has to fool that. And you can do the same story for an image from domain 2. So you can encode and then reconstruct, or encode and then translate with the losses to fool the other discriminator. So here's some samples from this model. I really like these. I was really impressed by these dogs, actually. So you get this dog as input, and then you want to translate it to the domain of sheepdog or husky. And what's cool is that the pose of the dog's face is roughly preserved, and even some parts of the background, like this grass. But clearly the breed of the dog is changing. And again, no supervision to do this. And the last one that I'll talk about is called Disco GAN. These things have some cool names sometimes. Where, again, you are learning an encoder-decoder, or like a mapping from domain A to domain B. You have some kind of pixel-wise reconstruction loss, and you also have domain classifiers that try to say whether a sample is from domain A or domain B, and you try to fool these samplers. And an experiment from this paper that I really like is car to face, or they have a series of these things where you have two things that are actually like really different. It's not two dog breeds, it's two completely different things. But the network invents some kind of alignment. So it figures out that, okay, faces and cars, they have a front and a back maybe, and you know, there's this manifold, there's this rotation manifold that you can use to align both data sets, and so it finds these alignments unsupervised. So there's also some practical uses emerging from these. So this model is called GraspGAN, and the idea is to use generative models to cross the reality gap. So it's easy to generate synthetic images of these arms grabbing things in a bin and doing manipulation tasks, but we actually want to learn on a real robot, and we can't actually like use graphics engines to produce photorealistic videos of these arms. So what do? We use a GAN to actually try to synthesize images. So going from simulation images to actual like photorealistic images, so that the policy that we learn can actually work in reality. So what does GraspGAN look like? You have some synthetic rendering. It's not realistic, but it has the right content. What your generator has to do is some kind of UNet. It has to like translate it into some photographic-looking image, but it also has to preserve the relevant content. So there's some segmentation that says where's the background, where's the bin, where's the arm, where are the objects. And then the discriminator decides whether that sample looks real or fake, as usual. The actual model is more complicated. They have more pieces, but this is sort of the generative modeling portion. Now I'll talk about text quickly. So typically, in neural machine translation, you need some paired data, at least some, that says the same sentence in both languages. But some language pairs don't have much parallel corpora. And so we ideally want a model that could be trained with non-aligned text. Some books in one and some books in the other. We learn models unsupervised, and then we get a translation model out of it. So the first paper is the simplest. It's just doing maximum likelihood as far as I can tell. We have, again, a shared encoder over the domains, language 1, language 2. The first objective is just denoising. So you take a sentence from language 1, encode and decode, and you do maximum likelihood on this decoded sentence to try to reconstruct. And then you do back translation. So take a sentence from language 1, you actually encode it and decode it, you sample in the other language, and given that sample, you back translate. And it turns out that if you do this, always doing back translation with the latest model that you have, this converges to an actually pretty decent translation model. Not quite as good as the fully supervised one, but like it actually works is the point. And you can also do things like semi-supervised training. You can also add GANs into the mix. So this is very similar in terms of overall design, but one piece that's different is that this sentence encoding can be fed into a domain classifier. So is this sentence embedding language 1 or language 2? And you want to fool this adversary. But overall, similar idea.
Cool. So now for a slightly different topic, although these generative models are really getting really good. So there's actually going to be a symposium and a workshop on meta-learning. So I'm just going to give you a bit of like the taxonomy and what do we mean by meta-learning. Again, like inputs and outputs and architectures here is not really the main element of what meta-learning is about. Meta-learning, by and large, is about the loss, and you can see it as a loss that models another loss. And I'll explain this in a second, but and there's like 3 ways to do meta-learning that people have come up in the maybe like last couple of years, although the term and the definitions are quite much older as well. So what is learning to learn or meta-learning? And I'm pretty sure it would be hard for us to agree on a definition. So maybe as an exercise, ask a colleague and see what they say. But for me, what learning to learn or meta-learning is to going beyond the train test, having this train test paradigm of training a machine learning model, where you have a training set and a test set coming from the same distribution. And it's really about, instead of having this distribution and having a sample from it and a model that hopefully generalizes, is having a sort of almost different task. And when you sample a new task, what you want your neural model to do is adapt and learn very quickly on the new task without needing to go through many steps of stochastic gradient descent, which we know is necessary for training things like ImageNet and so on. And with a great problem, you need great sort of data sets. And luckily, both Brandon and also more recently, like in a paper we introduced, a couple of data sets that are perfect for doing something called one-shot learning, which is an instance of learning to learn and meta-learning. And these are, you can see the data sets, they're kind of transposed MNIST in a way where there are many classes, but very few examples per class. So in a nutshell, what is meta-learning? What is different between learning to learn and just learning a model? So here is what learning a model looks like typically. You have some training data, and you have some test data. And what you're going to do is typically fit a model such that the likelihood of your model is maximized, and you estimate this likelihood by means of taking an expectation over batches of data from these data sets, right? So you sample a batch of data, this green, and you feed your model. You sample another batch of data, you feed your model, and so on until you converge. So meta-learning adds a twist to this, and it's only additive to this paradigm what we are so familiar with. Meta-learning does this. So in a picture, what meta-learning does is treats a whole training data and test data as a single instance. So you can think of a full data set of training and test examples is now a single training example, okay? And that's what Hugo and Chelsea also use this term that she calls, and he calls it meta-training set, right? So it's a training set of training sets, if you will. That's why it's meta. And then you're going to test your algorithm on a meta-testing set where there's going to be, let's say, some classes or categories or tasks that you've never seen. And in the more traditional way to expose the likelihood maximization problem, what you do is you have a model that not only maps from X to Y, but also takes in a S, what we call support set or training set, but it was too confusing to call it training set, so we decided to call it support set. And then this model takes this support set, and it's trying to fit for a batch of data this likelihood. So this is exactly the same equation, except there's this S. And this S is the training set that you should use. So here you have, let's say, a 5-way classification problem with 5 new classes, and this is going to be your S. And given this set S, what you want to do is have a model that will immediately classify these unseen examples very well, right? So you want the model to generalize, essentially. And so what you do is you sample first a task T, and you sample a few labels. So let's say these 5 categories are sampled from the 1,000 categories of ImageNet. And then given these 5 categories, you sample a support set that's going to be your training set or support set in the meta algorithm. And then you sample also a bunch of images that you must classify correctly. And this is how you would train one-shot learning from this learning to learn perspective, which is sort of how you actually train the model, right? This is the training procedure. But now, what kinds of models do we have? And here is where I distinguish these in three rough classes. The first is a model-based approach. And it's kind of cool because you can see this as a sequence-to-sequence model. So my model is going to be conditioned on a support set. These support sets are going to be, for instance, these 2 images of the dogs and which classes these dogs are. Like they say, this is a red kind of dog and this is a blue kind of dog. So your model is reading the dog image, the label, the next dog image, the label, and so on and so forth. It ingests this training data, and then what you ask the model to do is, at test time, you input an image and you ask it to classify it correctly, whether it's the blue or the red dog. And this is trained end-to-end, and there's a family of models that use this idea of model-based meta-learning. There's another family which has a better inductive bias for classification, which means they usually train faster and slightly better, which are metric-based. And here, the gist of the idea is that I'm going to have this support set now be sort of a training set that I keep in memory, so I know that this dog is blue, this dog is red, and maybe some other dogs, and so on. And I'm going to learn a metric or a function that allows me to compare a new dog, a new image of, let's say, the red dog, so as to, when I do the sort of nearest neighbor computation, I get the right label out. And I train this end-to-end. So it's kind of a differential nearest neighbor where there's deep features everywhere and so on. And again, there's a bunch of papers that use this metric-based approach to meta-learning. And the last one, which is perhaps the more closer to learn, is quite cool, is the idea that I'm going to get these pairs of this support set, like this dog is blue, this dog is yellow, and so on. And if I was doing traditional deep learning, I would maybe fine-tune a model with these new labels, although it's a bit tricky because you would need a new softmax layer and so on. But let's say you want to do that. Well, if you just apply gradients on these 5 images repeatedly, you're going to terribly overfit to these images. You're not going to generalize to these. So what these models do instead is they compute gradients, right? Knowing that gradients have the right information probably to fit a new model. But instead of applying the gradients to the model, you simply learn a controller that takes in these gradients and hopefully knows how to apply them to your model, such that after applying a few gradient steps to this model, they're going to classify a new image that they haven't seen in training of this small training set, let's say, of 4 images, and it's going to generalize. So the 3 have slightly different flavors, but there are a bunch of papers, and a lot of progress actually is being made, which is quite exciting. And then another kind of a different application of this idea of one-shot learning and learning from essentially a novel demonstration is this paper from OpenAI, which essentially took a trajectory or a demonstration, a single one, and said, look, I have a policy that needs to act on the world, and I want it to hopefully act like this demonstration that I'm giving to you. So it's very similar to one-shot learning, except it's for reinforcement learning. And the results, if the internet works, it's pretty good, actually. So giving it a single demonstration of touching some objects and whatnot, the policy learns by means of these, having many such examples of a single trajectory and what you intended to do and fitting your model. When you give it a novel demonstration at test time, it's able to sort of generalize and work quite well. So I think these models, as I said, there's so kind of active areas of research that there's both a symposium and a workshop. So I invite you to check that out because I'm sure there's going to be interesting talks and other aspects of meta-learning, like learning models architectures is another aspect that's quite interesting and quite relevant nowadays. So going beyond this meta-learning, there's perhaps, and this is kind of cool because it goes back to this kind of, what can neural networks not do or deal with very well, and should we fix it? And I think that's kind of a bit of really, like, graphs are just generalized sequences and generalized trees, so they're a very generic data structure. There are many tasks that you can think of being important to be able for your neural network to deal with a graph, but I think it's just, the main motivation is there's natural trend of this fixed input representation, these tensor inputs like images or videos and whatnot, sequential inputs, which are kind of maybe a special case of tensor inputs, and then graphs, which are this structure that is kind of hard to represent as a tensor. However, there are many models and proposals on dealing with graphs, which I'm going to describe here in a second. And also graphs, of course, like there's probabilistic graphical models, which are very interesting for medical diagnosis, for example. And there's some algorithms that operate on graphs that we would like to perhaps get some inspiration from and add it as maybe an element of our neural networks. If they could do reasoning on a graph, they might actually be able to do things that they can't yet. So again, this is going to be all about graphs and trees. And the architecture that I'll describe the most is this what we call message passing, which is the kind of architecture that deals very naturally with graphs. So going back to the inductive biases, we have spatial inductive bias for image models, the sequence kind of inductive bias of recurrence. For graphs, the kind of bias that we would like our neural networks to just have, not have to learn, but just inherently have, is the fact that if I rename nodes in a graph, the graph is the same. So if I have a function that takes some assignment of, let's say, v1, v2, v3, I would like, if I somehow vectorize this and I embed this graph, which is given to me as an input, I embed it to a vector or I predict something from this graph, I would like this prediction to be invariant that if I had renamed the nodes to something else, because the graph inherently is the same. It's the same as moving an object, it's the same object, right? So this is perhaps the main property we want to preserve. And there's actually an oral at NIPS from thinking about sets called deep sets that I also recommend you attend. So I'm going to describe a model that actually generalizes many models that have been proposed, which is great, because anytime you think about maybe empowering a neural net to deal with graphs, you might think about thinking about this framework and then seeing how you can improve it, which we called message passing neural networks. And I'm going to explain how this operates on a given graph as the input through an example, okay? So here, there's this graph. Let's say this is a molecule, and it has certain bonds. And this graph has, we represent each node of the graph has a vector. So each node stores a vector, and this vector is, let's say, a state, or and imagine it's a 100-dimensional vector, let's say. So that we have H1, H2, H3, H4, and H5. These are vectors that are sort of stored in the graph, in the nodes of the graph. And then we potentially also have edge features that are perhaps another vector or maybe a property, right? Like this is a strong bond or a weak bond. So the edges can also be parameterized by either a vector or maybe a category or a property. Depends on the models. So message passing neural networks have essentially a single phase that you repeat over and over, which is to pass messages to your neighbors. Very simple. And obviously graph invariant, which is the desired property. The first element is the message. The message essentially takes, so the message for a node V is going to be the sum of all its neighbors, so the incoming messages, and you're going to sum essentially some M. This M is a neural network, so it could be many things, like it could be as simple as summing the embeddings or maybe having an LSTM or something else. And it's a neural network that takes as input the representation of node B, so my own vector, the representation of my neighbor, and some sort of representation of the edge. Okay? And this creates a message that's perhaps a vector that it's incoming to my node. Now, the node itself, H, needs to update its state. So H computes a message, M, and it has a previous state, and then it just updates the state. This could be overwriting it, or it could be a GRU, and so on. And then finally, after repeating this process, you read out an answer from the graph. So here is how it looks like, right? So let's say H1 gets two messages, which will be two vectors passed through a neural network. And then it updates its state, right? So it was yellow, and now given this message, it decides to go orange. And so this happens throughout the graph. Every neighbor communicates with each other and so on through messages, and then they update their state. And you repeat this, and you can repeat this a certain number of times. This is an hyperparameter. And now, once you've repeated this, let's say 5 times, you will take these nodes, the representation of the graph, and then with these nodes, you're going to compute the answer, let's say, a property for a chemical element and whatnot. And this property here is 1.6 whatever, right? So this framework actually turns out to generalize a bunch of other frameworks. And in our case, we applied this for chemical discovery, but there's many, many papers, which I'm not going to go into detail, that deal with graph data, and that they propose certain algorithms, like, for instance, convolutional networks on graphs, turns out to have a specific form of message, of update rule, and of readout rule, right? And so many models that we see in the literature, for instance, interaction networks, another one that has this specific form, very generic, but actually doesn't do message passing per se. So you just do one message passing and that's it. Gated graph neural networks, a paper from UGA, also uses a GRU to update the state of the nodes and so on. So many of these models can be expressed with this framework, which is quite useful because it allows us to not be too confused about models that deal with graphs. I think this framework is general enough that you can place your model here. And I will finish with saying that with graphs especially, batching is extremely tricky because when you sample 10 graphs to form a batch size of size 10, let's say, these graphs are going to be different sizes and they have different connectivity patterns. So batching becomes quite tricky. And here is where choosing the framework and choosing the right, let's say, abstraction is what's going to make it or break it for you. I mean, implementing these models and batching them to be more efficient is important. And there are certain frameworks that provide things like while loops in TensorFlow. Also, PyTorch is very nice for graphs because the computation graph is dynamic, so you can just essentially load a neural network, load a graph and generate the neural network and so on. But these are sort of important technical aspects of graphs. Although if you don't care about speed, you can just do batch size 1 and be good with that, and then do the message passing stuff. So I'll leave the summary here and further reading, and then Scott is going to conclude with some very interesting topic on program induction, and then we're going to have some questions at the end. I think there's going to be 15 minutes or so, or 10. Thank you.
Okay, program induction with neural networks. So the research landscape that I will cover is basically like this. So the simplest approach is you think of the neural network as a program. So you somehow embed the program into the weights of your network. So like the cartoon version is you have some inputs, 2 and 3, and the network learns that 2 plus 3 is 5. So you give it the inputs, and the network directly gives you the outputs. So there's been a lot of models that do this over the past couple of years. The second major type is a neural network that generates source code. So you show it an example of an input and an output, or a set of inputs and outputs. You show it to the network, and the network actually produces the tokens of the actual program. The nice thing about this is if that program is correct, it's always going to work. It will generalize perfectly to any input. Whereas if your neural network is the program, there's a question of how well is it going to generalize to new inputs that it didn't see during training. But there's lots of work in both directions. And then there's the whole field of probabilistic programming, which I won't go into, but people are starting to try to integrate that with neural networks and in deep learning. And there's a variety of very cool looking frameworks to do that. So what are the building blocks? We'll have, again, discrete symbols like we had for natural language, but we can also think about the program itself, the text. We can look at execution traces of the program. So what did the program actually do when it was running? And we can also look at inputs and outputs of programs. And these can be mixed with perceptual data. It's not just bits, it's not necessarily just symbols. For architectures, they're mostly recurrent, but sometimes you will see convolutions, especially if there's pixels involved, like there's a visual front end, for example. And the loss, oftentimes, if you're predicting discrete outputs and everything is differentiable, you can just use cross entropy as if you were doing language model. But if it's not differentiable, then you have to do RL. So one of the first papers that got people really excited about baking programs into neural networks was called Learning to Execute. It's a very bold paper. The idea is you give it a simple Python program. It can even have like loops or simple arithmetic. And in some cases, it can actually correctly predict the output of this program. So people were really impressed by this. Of course, you can't really completely learn Python, but the fact that it worked at all got people very inspired. Some people also thought about how to learn more parallel programs. So instead of doing just recurrent networks, you could think about how to use ConvNet. So there's this architecture called they call neural GPU that is based on repeated iterations of convolutional gated recurrent units. And they can learn algorithms like binary addition and multiplication that can generalize to bigger problems than it saw during training. And if you look at the animations of this thing running, it looks like a cellular automaton. On YouTube, you can find them. It looks very trippy. Another important paper was the neural Turing machine, or now they're being called differentiable neural computers. Here we start to see the addition of more structure to the neural network used for program induction. And the most important kind of structure that we see here is the addition of a memory module. So at every time step of processing for some problem, you get to write to a memory and also read from memory. And so this network learns a policy of how to read and write in order to solve these problems. Other people took the approach of actually learning the interpreter of a program. So in this paradigm, the user will fill in some parts of the program, like this would be bubble sort in the 4th programming language. You supply most of the lines, but maybe there's some blank that you want the network to fill in. So what they do is actually make this programming language differentiable so that when there are these blanks, the neural network learns to fill in the missing behavior to actually reproduce the desired behavior. And it has interesting features like a soft version of a program counter that models its uncertainty about where it actually is in the program execution. And this is at ICML. Another way to add structure into these models that embed the programming of the network is to look into hierarchies. So this neural programmer model, neural programmer interpreter, what it does, it's basically a router from programs to subprograms conditioned on the environment. And so we show that it can learn simple algorithms like addition or sorting that generalize to problems beyond the size it saw during training. And on the right, you can see like the hierarchical execution trace as this thing does addition. One drawback is that you, of course, need supervision about, okay, what subprogram are you going to call at each time step? So you need detailed execution traces. There's been steady progress since that paper was written on reducing the supervision. So exploiting recursion and also exploiting flat traces rather than detailed hierarchies to train these things in a much more efficient way. And there's also been progress in deploying these ideas on actual robots. So a slight variation of this model called neural task programming allows teaching pick-and-place algorithms, pick-and-place style manipulation algorithms to robots. And again, they show that they have very nice generalization properties. So in an actual robot, they can show that this hierarchical program reduction model can actually do a much better job than flat models of sorting objects, and they can sort many more of them. So you see much better generalization. And so these things are actually starting to bear fruit in practical problems. Now I'll move on to approaches that actually generate code in some form or another. There's been several very cool papers that have some kind of domain-specific language that they use to attack a particular problem, and they generate programs in this DSL. So in the DeepCoder paper, they're interested in programs that manipulate arrays of numbers. And these are the kinds of things you might see in simple programming contests, let's say. And so the programs that are being considered are just kind of straight line programs, just like a sequence of API calls, basically, of things that manipulate these arrays. And so you're going to find the right sequence of API calls that map this input to this output, or a set of inputs to a set of outputs. So the approach that they take is to train a neural network to predict attributes of the program. Like, does this program have a call to filter or sort or reverse? Or does it have this particular little substring in the program? So there's this long attribute vector characterizing things about the program. It's not a full specification, but the point is that when you want to use classical search-based methods to actually find the right program to accomplish this input-output mapping, you can use the neural network's attribute predictions to search much faster, to prune the search space, basically. And so they show that you can have big speed-ups in terms of the time it takes to actually find the program that correctly maps inputs to outputs. So this is called DeepCoder. Another approach actually generates the tokens of the source code directly from the program. So again, you have input-output. You could imagine this is like some rows in Excel, and you want to canonicalize these names and put them in last name, comma, first name order, let's say. So given these inputs and outputs, you want to be able to actually generalize to some more names. And so the program is some string, this sort of string manipulation program. It's a domain-specific language that these authors created for this problem. And so the task for the neural network is look at these input-output pairs and then generate this program. It's called robust fill. So the model is actually fairly simple and elegant. You just encode all of your I/O pairs and the previous tokens of your program, and then predict the next token of your program, where the tokens come from this domain-specific language. And the really cool thing that they show is if you compare against Excel's previous flash fill, which is not based on neural networks, if you have no mistakes in your little training set, maybe flash fill's a bit better. But this neural net model is almost as good. If you have one mistake, flash fill will just break, like the typical like old-fashioned brittle methods, because they're not robust to noise. But the neural net methods actually degrade very gracefully. So to me, this was like a very, very inspiring, because it's the first proof that neural program induction can actually be useful. Beyond those approaches, people have used, are more and more integrating neural nets into probabilistic programming. So if you think about graphics programs that produce things like 3D faces, 3D shapes, 3D human poses, we can use these graphics programs to generate lots of data. But then suppose that you have an image and you want to find the program that would actually reconstruct it. And once you have that program, you can tune the knobs and re-render with different poses or different lighting that you might want to do for things like animation. So where do neural networks fit in this pipeline? So for these probabilistic programming languages, we have a scene language and a renderer, which may not be differentiable. It could be some very complex system, which produces renderings, and then you have some observed image that you want to match. You can use features of a deep neural network to actually match, to see how well these renderings match up with the actual image that you have, and to help guide your search over programs that would actually reconstruct your image using this, this graphics program. So that's it for neural programming. Now I'll just go over some brief conclusions and thoughts about the future. So one thing that we saw is that deep autoregressive models and convolutional nets are now ubiquitous in production, and they're already useful in a lot of consumer applications. So anything with images like image search, or with autoregressive models, machine translation, text-to-speech. I mean, these are all in products. Also we saw that inductive biases are really useful. So in deep learning now, we're really against hand engineering things, like specific features, but it's still really valuable to think about architectures with the right biases that still have some flexibility to actually learn the weights, like spatial invariance in CNNs, or time recurrence in RNNs, permutation invariance in graphs. If you're careful about choosing the inductive biases, you can gain a lot in performance. We saw that like simple tricks like residual networks, skip connections, just gave us a quantum leap in performance, and I think there will be new ones that will be discovered that in hindsight may look obvious, but we don't have yet. I think adversarial networks and unsupervised domain adaptation, they will have more and more interesting applications on phones for fun things like style transfer. I think we think that in meta-learning, or because of meta-learning, more and more of the life cycle of a model, from training and validation and testing, this will be just part of an end-to-end training process. So everything we do now will start to look like the inner loop of some more general thing, and then some more general thing, and so on. And then I think we'll see that, we think that program synthesis and program synthesis combined with graph networks will be very important, and hopefully find more real-world applications like we saw with robust fill. Okay, thank you.
If you have questions or comments, we have some time. Otherwise, stop by and yeah, like there's questions somewhere. I think there's mics on the sides if you want to ask questions. All right, so then it was very clear. All right, last chance. No? Yeah. Yeah, you can shout. We'll repeat. Yeah, the slides, we'll put them like available soon. We'll tweet or something. So look for it, yeah. Okay? All right, so have some coffee. Thanks for coming so early. Thank you.
Thank you.